Quantum mechanics is the most precisely verified theory in human history, yet it contains a glaring foundational gap. This is the measurement problem. The Schrödinger equation describes a world of perfect determinism, where particles exist as waves of overlapping possibilities. But the moment we measure that system, the wave vanishes. It collapses into a single definite point, without any mathematical explanation of how or why. Early physicists lacked a mechanical cause for this event, so they relied on a guess. They suggested that the act of human observation or the presence of consciousness itself triggered the collapse. For 90 years, this missing mechanism forced physics into a corner. It required a choice between bizarre philosophical workarounds, parallel universes, hidden variables, or the idea that reality only exists when a mind is there to perceive it. Daniel Toupin's 2026 framework provides the missing link. He demonstrates that the transition from quantum to classical states is a mechanical process that requires only heat and mass. In this light, the conscious observer appears as a historical placeholder, a necessary fiction used to mask a century of missing thermodynamic physics. To find the physical cause of collapse, we have to look at the three interacting components of any experiment: the quantum system, the measuring tool, and the surrounding environment. Early foundations ignored the scale of the measuring apparatus. It is a macroscopic object containing trillions of particles, which means it possesses a specific measurable temperature. When a delicate quantum superposition finally touches this massive macroscopic thermal bath, it is completely overwhelmed by thermodynamic forces. Temperature is the catalyst. It forces the quantum realm to resolve into the classical reality we experience. This process is known as Haar projection. The massive thermal environment acts as a filter, stripping away the chaotic quantum fluctuations of the central particle. Environmental pressure forces the system into a stable mathematical state called a gauge singlet. This happens nearly instantaneously. The thermal filter acts in a fraction of a femtosecond, a timescale dictated by the ratio of Planck's constant to the room's temperature. This thermodynamic filtering is wave function collapse, a mechanical transition driven by entropy and geometry. If the collapse is deterministic, we have to explain why we use Max Born's rule of squared probability to predict the outcome. Toupin's derivation shows that the Born rule is a mathematical necessity. Haar's uniqueness theorem proves it is the only probability rule compatible with the fundamental symmetries of the universe. Quantum collapse is a mechanical consequence of the laws of thermodynamics. It does not require a mind. It only requires a thermo-environment. If the mechanism of Haar projection is mathematically certain, we have to account for why the final outcome appears random, why an electron spins up instead of down. The specific result is predetermined by the complex microstate of the 10 to the 23 particles that make up the thermal environment. Quantum randomness is thermal ignorance. Like a coin flip, the result appears random only because we lack the data to track the trillions of surrounding molecules that influence the outcome. This redefines the observer. In physics, an observer is any thermodynamic system possessing mass. Mass is the physical requirement for experiencing proper time and generating an entropy-increasing record of an event. The reliance on human perception has been replaced by the geometric structure of the vacuum. The universe is a unified, deterministic mathematical structure. It does not wait for us to look at it to exist.